Welcome everyone to the Global Water Futures Core Modeling and Forecasting Team's Topical Webinar Series. My name is Praveen Rokaya. I'm the Science Coordinator of the Core Modeling and Forecasting Team. It is my pleasure to present you today a webinar on vanishing weekly hydropeaking cycles in American and Canadian rivers. Today we have Dr. Stephen Derry from the University of Northern British Columbia. Dr. Derry is a professor in the Department of Geography, Earth and Environmental Sciences and in the Natural Resources and Environmental Studies graduate program. As of July 1, 2019, Dr. Derry holds a Young-Cert Rio Tinto Senior Industrial Research Chair in Climate Change and Water Security with a 5-year research program focused on Nechaco watershed. Dr. Derry's background is in atmospheric sciences. He has a degrees from York and McGill University. He also held a postdoctoral position at the Columbia University in New York and was a visiting research scientist at Princeton University in New Jersey. Dr. Derry investigates the consequences of climate change and water management on the water cycles of northern and alpine region. A major aspect of this research is to better monitor, understand, and project the water temperature and stream flow trends in major watersheds based on observation data, remote sensing, and numerical simulations, which I believe Dr. Derry will be highlighting partly today. Without taking much time, I want to kick off this webinar by thanking Dr. Derry for accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Derry, the floor is yours.
Excellent. Well, thank you so much for that introduction. Thanks to you, to Al, and the GWF Core Modeling and Forecasting team for the opportunity to present today. Really appreciate this. And as was just introduced, we'll be talking about hydropeaking today in American and Canadian rivers. And particular interesting finding, I think, anyway, is that you'll see some declines in terms of the hydropeaking intensity across parts of North America. I want to acknowledge my co-authors on this work. So Dr. Tricia Stadnick at the University of Calgary, Dr. Tara Troy at the University of Victoria, as well as Marco Hernandez Enriquez at UNBC. And as well, I'm talking to you from the UNBC campus in Prince George, which is on the traditional territory of the Klikletene, which in the Carrier language means where the two rivers meet. So the confluence of the Nechaco and the Fraser rivers. This picture is not of the Fraser. This picture is actually of the Natigi control structure, which is where water is diverted from the Churchill River Basin into the Nelson. And we'll be presenting some results on the Nelson River and other, of course, regulated waterways across parts of Canada and the USA today. So a couple of background slides, and you may have seen this paper actually by Grill et al. Published in 2019 in Nature. And essentially they were mapping all the free-flowing rivers, and of course the regulated ones as well, across essentially the entire globe. And what you do see here is a lot of red into the green colors. So this indicates waterways in which essentially their connectivity status index is less than 95%. It's a scale that you see at the bottom there, indicating that these systems are essentially fragmented, regulated, so impacted in part by hydropower dams. So a good portion of the globe actually is affected by regulation. And a main finding of this study was that about 37% only of the global rivers that span 1,000 kilometers or longer are actually free flowing. And that includes, of course, many regulated rivers in parts of North America, if you see on the top left, particularly in USA, into parts of Southern Canada, even Northern Canada. So this study by Grill et al. Was actually building on the previous work by Dionysius and Nilsson, where they were mapping essentially those systems across the northern third of the globe that are essentially fragmented or regulated. And they had a scale, and there's three different, I guess, bins, if you like, in terms of fragmentation and flow regulation. The colors are at the bottom right of the slide. So unaffected is in green, Moderately affected is in yellow, and then sort of the reddish color is strongly affected. Again, these are systems that are either fragmented or regulated, or a combination of both. So across North America, you do see a lot of rivers that are essentially regulated or fragmented, particularly in the US. The outlier in the US, and I should mention, these are all river systems that drain to the coastal ocean with a mean annual discharge pre-regulation of 350 cubic meters per second or more. US, the only system that is not regulated in any way is actually the Pascagoula. So it's a sort of an exception in terms of all the major systems in the USA. But we do see a number of systems in Canada as well that are heavily affected. So it includes the Great Lakes St. Lawrence system, the Nelson River system, the Churchill, and in Western North America, the Columbia. And the Fraser and the Mackenzie are moderately affected. So in the Fraser, we have the Nechako, which is dam. And then, of course, in the Mackenzie, we have the Peace River that is dam. So these, on their scale, become essentially moderately affected. All right, so you may have heard the term hydropeaking. If you have not, here's an example of a hydrograph showing that hydropeaking process. This will typically appear in regulated systems where we have hydropower dams. The example that we have here is actually for the Manitoba, or Manitoba's Nelson River. This is in the lower reaches, where we have essentially the kettle generating station. The top panel indicates essentially the hydrograph with mean hourly stream flow. And it's a period of 1 week, between the 3rd of July to the 10th of July, 1984. And of course, hydropower demand and production will tend to fluctuate across one day and will tend to ramp up during the day. So you do see, whoops, going back here, essentially on the 3rd of July, for instance, in the early morning, we see the ramping up of discharge at the kettle generating station as we have, of course, hydropower demand increasing during the day, and then that decreases during the night. So this leads to very pronounced diurnal fluctuation, right, that you see in the hydrograph tied to hydroelectricity production. You also see, actually, if we look at the 7th into the 8th of July, that we have a reduction in the flows at the kettle generating station because it's the weekend. So we have less, essentially, electricity generated during the weekend. So we have a pattern that is emerging here of strong diurnal fluctuations, but also weekly fluctuations. And moving to the hydrograph that you see at the bottom here. So again, this is the kettle generating station in 1984. Now we're looking at the entire year where we have daily discharge. And again, you see these really strong fluctuations, right? So we have high flows during the weekdays, followed by low flows during the weekends. And that leads to a very marked weekly cycle. And so this is the feature that we want to highlight here is hydropeaking, which is tied to hydropower production and leads to very strong or robust diurnal and then weekly patterns. I just want to highlight that the red bars here indicate the period of the 7 days at the top of the hydrograph on the lower annual hydrograph here. All right, so this work was actually motivated by some work that Trish and others in the freshwater team for BASIS, Team 2, did, where we were looking essentially at the effects of climate change and flow regulation on the total flows into Hudson Bay. And you see a hydrograph that we created. This was part of a publication that came out in 2018, where we essentially divided up the rivers that are not affected by regulation. So the red and the green hydrographs versus those that are actually regulated in blue and then in black. So we have an early period, 1961 to 1988, and then 1989 to 2016. I should mention these hydrographs take into consideration the day of the week. So what we do see, of course, over time in the regulated system that we're losing that seasonality, right? We have essentially a flattening of the hydrograph, really clearly emerging, tied again, because most of these systems are regulated for hydropower production to when demand is highest, often, of course, in the winter in parts of Canada. Those hydrographs also show, though, very clearly a weekly cycle, again, tied to that weekly cycle in hydroelectricity production, with high flows during the weekdays, followed by the low flows during the weekends. All right, so we wanted to see how common this feature in terms of the weekly periodicity in regulated systems was across parts of North America. We want to expand, essentially, our study from those rivers flowing into Hudson Bay to essentially across most of North America. Our first goal for this study then was actually to develop a weekly hydropeaking index, what we'll abbreviate as WHI, that quantifies weekly periodicity in stream flow. So we could not find an actual study that had explored this in terms of using one metric to identify weekly hydropeaking. And then the second objective was to apply our WHI to 500 sites across Canada and USA to identify patterns and emerging trends in weekly hydropeaking. So we made use of, as I mentioned, of 500 sites across essentially, I don't know if we could call it Southern Canada, but Canada south of 60 degrees north, and then across the entire USA. Most of the data, of course, comes from the Water Survey of Canada, and in the US, we have the United States Geological Survey. Having said that, we were actually quite fortunate in terms of attaining some proprietary data from about 12 utilities and other agencies. So that includes NB Power, Hydro-Quebec, Ontario Power Generation, Evolugen, we have BC Hydro. In USA, we had essentially the International Boundary and Water Commission for sites along the Rio Grande, about 14 sites from the Tennessee Valley Authority, another 10 from USA's for the Cumberland River system. So we did attain quite a bit of additional data aside from publicly accessible databases. Our study period spans 1920 to 2019, so a century. We'll be presenting, however, results mainly for 1980 to 2019, a 40-year focus period. The average length of the time series is 80 years. So spanning up to a century, the minimum is 24 years. And we have a combination of regulated and unregulated systems. We really did want to compare and contrast systems that are heavily dammed versus those that are not. The color scheme here indicates the power grid interconnections. So in the west, we have the Western interconnection towards the, I guess, the Alberta-Saskatchewan border eastward. We have the Eastern power grid interconnection, and then in Texas, they're independent. They have their own interconnection, ERCOT. So I'll come back to that a little bit later in our discussion as the possible influence of the power grid interconnectivity on the results that we'll be presenting today. Well, like I mentioned, we could not find actually another study that had really defined a weekly hydropeaking index. We developed our own, and it has two terms. We have a time domain terms, TT, which is the fraction of weeks in a given year for which the low flows for 2 consecutive days is less than the 7-day corresponding weekly mean, which for regulated systems, essentially those that are regulated for hydropower, which tend to occur on the weekends. So the Saturday-Sunday combination, SS, relative to the weekdays. We have a frequency domain term, TF, which is the explained variance of the 52nd harmonic of a discrete Fourier transform applied to the time series of the daily discharge. And of course, the 52nd harmonic represents the weekly time scale. We multiply the time domain term with the frequency domain term and then times a coefficient B taken as 10, and then take the base 10 logarithm. The WHI will tend to vary from, say, -3, -4, indicating essentially a strong annual cycle in the discharge versus positive values, which will essentially indicate a strong weekly cycle tied to weekly periodicity and hydropeaking. So maybe we're getting a little bit ahead of ourselves, but you see a result here for 3 systems spanning the minimum, the median, and the maximum WHI. So the maximum is actually the Smith River in Virginia at Philpott, which tops the scale at 3.783 in our WHI. So you see here the mean daily flow for 1980 to 2019 in black, again showing that strong weekly periodicity, again tied to hydropower production. The St. Croix River in Maine, New Brunswick, essentially is at the median, so close to zero. And the Namakan River is a lake-rich system. It actually drains into Rainy Lake. It's part of the Winnipeg River system. And because of that, it has a really strong annual cycle. So that's the blue hydrograph. And so it's the largest negative value at minus 3.168. Just to give you an indication of the WHI values that we'll be reporting here. So in terms of the analyses, we did some temporal gap filling using the mean daily discharge over the period record. And we're going to be looking at the total annual discharge Q as well as the WHI computed for each site and each year when there's less than 10% of the daily data missing at any given site in any given year. And then we'll generate some results for 1980 to 2019, as well as for each decade from the 1920s up to the 2010s. We'll be presenting maps of the WHI. We'll be looking at trends, linear trends, using the Mann-Kendall test, and we'll assign a statistically significant trend as P less than 0.05 for 1980 to 2019. We'll also look at dispersion in day of the week flow. So we'll be looking at that a little bit later in this presentation. Also correlations between annual WHI and Q. And then we'll look at the downstream signal propagation on the Peace River using the WHI as well as cross correlations for 1980 to 2019. Again, that's sort of focus period. All right, so we'll jump into some results now. And there's a lot of maps I'll be showing here. The first one actually shows what we call the WHI climatology. And it's based on a color scale. So some people don't like the rainbow scale. Apologies for that. But essentially the negative values, so the purple into the blues indicate negative WHI. So no hydropeaking, really strong annual cycle in terms of the flows. Whereas values that are positive indicate some hydropeaking, with the intensity increasing as we get into the yellow, orange, and the maroon colors. The maroon colors indicate those sites with a WHI of 3.0 or higher. So we do see a number of clusters, of course, with high hydropeaking sites. And I'm not sure if you can see my mouse here, but certainly in the southeastern US, we have a number of heavily dammed systems. So that includes the Alabama River. We have the Chattahoochee River as well, with two maroon symbols representing two sites on the Chattahoochee. The Tennessee Valley and its tributaries are heavily dammed by the TVA, the Tennessee Valley Authority, as well as the Cumberland River. So again, a cluster of high hydropeaking sites. The Smith River in Virginia. Moving into Canada, we have the Niagara River, of course, which is heavily regulated. In other parts of the Great Lakes, St. Lawrence system, we have the Montreal River, as well as some rivers, the Mississauga and the Montreal River draining into Lake Superior and Lake Huron. The Abitibi River in Northern Ontario, that's part of the Moose River system. La Grande Rivière up in Northern Quebec, of course, the Nelson River in Manitoba. And moving into the west part of Canada, we have the Kananaskis River, that's part of the Bow River system. The Columbia River, which has several major dams, Mica Dam, Revelstoke Dam, Grand Coulee, the Dalles. So those all show up very high on our hydropeaking scale. And then the Colorado River, of course, and mainly the Hoover Dam and the Glen Canyon Dam. We have data for the Lees Ferry, so slightly downstream of Glen Canyon Dam. So those two rank highly on our WHI scale. I should mention as well that, of course, those systems that are not regulated, particularly if you look at around Hudson Bay, these systems tend to have really large negative values. So again, these are lake-rich systems, lots of wetlands, and the Essentially, discharge is dominated by the annual timescale. So we have really large negative values in rivers that are not affected by regulation. Another point that we wish to highlight is that the size of the circles indicate the 2 days, 2 consecutive days with low flows. And that, for the large symbols, indicate the weekends, Saturday, Sunday. So you see the definition of the 2-day combinations here on the bottom left of this map. So what we want to highlight here is that typically the higher the WHI, the closer to the weekends. If not, on the weekends, we see the low flows. So indeed, size indicates really low flows, typically in regulated systems. In fact, if we look at the table here, and we see the percentage in terms of the distribution of low flow days with the 7 possible combinations. So 31% of the systems that we examine out of the 500 that we have in our study show the Saturday-Sunday combination with low flows. So that's more than twice the expected value. If everything was randomly distributed, would be 14%. Even the Sunday-Monday combination occurs at 15.6% of the site. So again, above the expected value, whereas the Thursday-Friday and the Friday-Saturday combination occur less than 10% of the sites. And then if we look at the WHI, that's the last column on our table here. We see that the Saturday-Sunday combination on average has a WHI of 0.33, whereas the other 2-day combination, we have a WHI that averages close to 0, if not negative, slightly negative values. So pretty interesting to see the distribution of sites with hydropeaking rivers across many sites, of course, as you see here across the USA and Canada. All right, so a table of the top 10 scores in terms of WHI. First, you'll see that most of these values, the top 6, are actually 3 and above. These are all at sites that have hydropower facilities, and essentially are mainly located in the southern US, particularly the Smith River in Virginia. So we have 2 sites along the Smith River, 2 sites along the Chattahoochee River in Georgia. So Buford Dam is just northeast of Atlanta. We have the Ottawa River near Alatoona Dam, and the Colorado River with the 2 sites, the Hoover Dam and then the Lease Ferry, so just downstream of Glen Canyon Dam. We have 2 sites in Canada, so the Nelson River. Of course, we have several hydropower facilities, particularly, say, the downstream portion downstream of Stevens Lake. So we have the Kettleland Long Spruce Limestone generating stations. So Nelson River is the top Canadian rivers, I guess, on our scale at 2.916. And then the Niagara River, of course, spans the international boundary between Ontario and New York at 2.9. And the last column here represents the 2 days with the low flows. And again, this occurs on the Saturday-Sunday combination. All right, so looking at time series, and this is the advantage again of the weekly hydropeaking index that we've developed, is that we can look at time series of the hydropeaking intensity. So there's a lot of information here. Let's go through the different panels starting at the top. Panel A represents the mean, the median, and then the discharge weighted WHI. So discharge weighted, essentially we look at the WHI for each site and multiply that WHI value by the annual discharge, and then divide the total, once we've done the sum, by the total discharge as well. This is just to get a sort of a measure of the total volume of the river discharge that is affected by hydropeaking. So we start off in the 1920s. If you look at the top left here, the black and the red curves tend to mimic each other. So the median tends to follow the mean. And we start off by negative values, and then the WHI tends to increase well into the 1950s and then the 1960s. Thereafter, it is fairly stable at near 0. And then it starts decreasing in the 1990s up to the 2010s. And we'll come back to that actually a little bit later in this presentation. The discharge weighted WHI starts off largely negative and continues to increase into the 1980s. And the main influence there are the large hydropower facilities developed actually in parts of northern Canada during that period. So for instance, the Churchill Falls powerhouse in Labrador in the 1970s. We had this Lac-Angevillard and all the James Bay hydroelectric facilities coming online in the 1980s. But we also see that the WHI discharge weighted actually declines from the 1990s onward. We also looked at the number of sites in the top decile. The top decile are values of WHI of 2.117 or higher. Of course, we start off with low values, both in terms of number of sites and the percentage of sites in the top decile. It peaks in terms of number of sites at about 80 in 1963 and then in the late 1970s. But you do see a decline, particularly actually from the year 2000 onward. In the year 2000, we had about 60 sites or so in the top decile. And by the time we reached 2019, we had maybe just above, say, 15, maybe 16 or 17. So really a significant decline in terms of number of sites in the top decile, both in terms of the numbers and the fraction. And then finally at the bottom is actually the annual maximum WHI value, which starts off at about just above 2.5 or so, and then increases rapidly, and then is fairly stable throughout the 1950s and 1960s, and is slowly decreasing over time, starting in the 1990s onward. The top score overall, 4.752 for the Smith River in 1955. And you see at the bottom right, this is a plot taken from USGS of the hydrograph, the daily hydrograph for the Smith River in 1955. Very, very regular pattern that you see emerging. And that leads to that top score that we saw in our WHI. Well, again, we could look at time series. We could spend the whole day looking at time series of WHI for the 500 sites that we have, but let's focus on 6 in northern Canada. So the Abitibi, which is part, again, of the Moose River system in northern Ontario. We have the Churchill. This is the Churchill River in Labrador, the Churchill Falls powerhouse. Lac-Angevillard at LG2. The Moose River in northern Ontario, the Nelson River in Manitoba, and then the Peace River at Hudson Hope. So this is just downstream of the 2 dams, W.C. Bennett and Glen Canyon Dam. The baseline for all of these plots is a WHI of 0. So anything above the baseline indicates hydropeaking, and then below that indicates negative WHI, so no hydropeaking. And the vertical red lines indicate the year when dams or hydropower facilities were commissioned. So we can look at, say, the Churchill River and essentially large negative scores in the 1960s up to 1970. And then the Churchill Falls powerhouse facility came online in 1970, late 1970 to 1971. And you see the WHI really responding. As soon as we have essentially that regulation of the flows on the Churchill River, we see the WHI really spiking. And in fact, it switches from a large negative number to a large positive number. We also see another interesting feature, actually, which I wish to highlight, and I'll come back to this a little bit later, is in, say, in 1997, I believe there's a really abrupt decrease in the WHI, and this is related to water management at the Churchill Falls powerhouse. So I'll come back to that a little bit later. But you do see our WHI responds on as soon as we do have regulation. For instance, at LG2 in 1980, that facility came online. We see the WHI again switching from large negative to positive values. The same at the Nelson River, and then for the Peace River just downstream of the W.C. Bennett Dam. The Abitibi and the Moose were at least regulated in part in the early 1900s. And so you don't see that abrupt change within a time series right away. Well, we can look at the temporal evolution of the WHI across the decades. So these are similar maps, all using the same color scale and WHI. And of course, we're limited a little bit now by the data availability. We have fewer sites starting in the 1920s. Here we're plotting data when we have a minimum of 5 years across that decade. Again, sort of the yellowish, the orange, and the maroon colors indicate positive WHI, so hydropeaking sites, and then the blues and the purples indicate no hydropeaking. In the 1920s, you're already seeing actually some sites in Canada with hydropeaking. So the Abitibi River, the Rainy River, the Winnipeg River, and then the Assiniboine River. So already we have sites that are showing evidence of hydropeaking. The bold number at the top right of the maps indicates the number of sites with WHI greater than 3. So you see that increasing as we go through the decades here. Indeed, in the 1930s, now we see the emergence of more hydropeaking sites. The sites along the Rainy River, Winnipeg River, and Abitibi River actually are scoring above 3 now. We have sites in New York State, into Pennsylvania as well, and then a couple of sites as well in South Carolina. Moving on to the 1940s and 1950s, we see now a rapid expansion of hydropeaking sites. That includes actually the Humber River at Deer Lake in Newfoundland. We see a large number of sites now appearing in New England, into New York State, as well as Pennsylvania. In the southeastern US, we see, particularly in the 1950s, now the emergence of all the Tennessee Valley Authority sites. We have, I think there's 29 or 30 facilities that they have in the Tennessee Valley. So we really do see the emergence of that, those hydropeaking sites on our maps, particularly in the 1950s. In the 1950s, you also see the emergence of some sites along the Ottawa Valley. So these are actually tributaries to the Ottawa River. Again, the Abitibi River, we have the Nipigon River as well, that drains to Lake Superior. We start seeing some hydropeaking as well in the Pacific Northwest in Washington State. And in the 1940s and 1950s, you do see essentially the Hoover Dam with a score of 3.0 or higher. You also see really at the top right, the number of sites with greater than 3 WHI is now at 18. Moving on to the 1960s and 1970s. The 1960s is really the decade I would call as the apex of WHI in terms of the scores of 3 or higher. A lot of sites with really strong weekly hydropeaking cycles. Now we see the emergence of other sites across Quebec and Ontario. For instance, we have sites, the Mississauga River draining into Lake Huron. We have the Montreal River draining into Lake Superior. We still have the sites like Nipigon River, Rainy River, and the Winnipeg River. We see the continued presence of highly hydropeaking sites across now the Alabama River, the Chattahoochee, the Tennessee Valley, as well as the Smith River. We see the Red River across the border between Texas and Oklahoma. We see some rivers draining the Ozark Mountains as well, and the Colorado River as well. In fact, in the 1970s, of course, Glen Canyon Dam came online, I think in 1970 or 1971. So we see the rapid emergence of that site in the 1970s, above 3. So quite a bit of regulation there on a weekly basis. And we see the continued expansion of regulation in the Columbia River system, and as well now the appearance of regulation and hydropeaking in the Peace River system. 1980s and 1990s, now we see essentially the continued presence of hydropeaking. But what is interesting, and I should mention this, of course, going back to the 1970s, we had the Churchill River in Labrador that came online, so that facility, and we actually see a decline in terms of the number of hydropeaking sites in Quebec. So most of the power sold by Nalcor is actually going to Quebec, and there's probably a strong connection between that and the essentially decline of WHI at other sites across Quebec, in that we had now a 4,000 plus megawatt facility feeding into the Quebec system, possibly alleviating the weekly hydropeaking cycles across other parts of Quebec, and maybe even New England and New York State. So the number of sites is fairly stable in terms of WHI greater than 3 at 13 and 15 during these 2 decades. We still see a number of highly hydropeaking sites across the southeastern US. That continues in the 1990s, as well as those rivers draining into Lake Superior, into Lake Huron as well. Of course, in the 1980s and 1990s, we see the emergence of la Grande Rivière, so LG2, and the Nelson River, of course, which is another highly hydropeaking site. And then what is really interesting, I think, is what happens in the 2000s and then the 2010s. By the 2010s, we have only 3 sites now with WHI greater than 3. We've lost a lot of those highly hydropeaking sites. We have a lot of green, and the symbol sizes have actually declined, indicating really the absence now of really highly hydropeaking sites across both the USA and Canada. And we'll come back to that a little bit later, because it's an important finding, we believe, and we'll try to discuss what may be the reasons for that. But again, if I just flip back between slide number 16 and slide number 17, if you focus on the right-hand side, you do see a really abrupt change. Of course, we're spanning 20 years now in terms of the 2 maps, but you see a rapid change from a lot of hydropeaking sites to those that are not in the 2010s. So we can look at this in a different way here, just looking at the bin distribution of the WHI for each of the decades. So we have data here for the 1920s up to 2010s. The color scheme for this graph is not exactly the same as that used for the spatial plots, but we're trying to mimic that, indicating essentially the purples and the blues, negative WHI, so no hydropeaking, the yellows, the orange, and to the maroon colors, which are at the bottom of the bars here, indicating highly hydropeaking. We start off in the 1920s with relatively low amounts of hydropeaking sites. About 7% of the sites are at a score of 1.5 or higher. And we see an expansion of that, as you see at the bars with the yellows now covering up to 21% in the 1960s. So again, that's sort of the apex for hydropeaking across southern Canada into the USA. And then we see the decline or the demise of hydropeaking into the 2000s and the 2010s. In fact, the fraction or the percentage of sites with essentially a hydropeaking value of 1.5 or higher in the 2010s is about 7%. And that is almost the same value that we saw in the 1920s. So certainly a big shift in terms of the number of sites with hydropeaking cycles, particularly going from the 1990s into the 2000s and then into the 2010s. Well, as I mentioned, we have WHI time series for now 500 sites, and we can apply essentially the man-candle test to look at linear trends in our WHI time series. So this is what we did, and now we're showing results only for 479 of the 500 sites. We applied the man-candle test to those where we had at least 30 years of data. So you see a lot of blue triangles on this map. So the blue triangles indicate negative trends. The larger the symbol, the larger the trend. So it's by magnitude. You see the scale in the legend. The red triangles indicate essentially positive trends. And then the circles around some of the triangles indicate whether the trends are locally significant. So that's the blue triangle, circles. No, not the blues. Sorry, I'm getting confused with my symbols. The green circles around the blue triangles indicate significantly declining trends. at the local scale, so P less than 0.05. And then the pink circles indicate those that are globally significant. So we use an approach following Wilkes 2019 to determine the global significant trends. And as the numbers show in the box on the right, we saw a predominance in negative trends. So 138 of the 479 sites, so close to a third, are showing locally significant declines, whereas we have only 28 with positive trends. So of course, most of these sites are highly hydropeaking. So if you would go back to the climatology, you'd see a really good correspondence between the declines and those that actually have, in terms of the 1980 to 2019 climatology, values of WHI greater than 0. So again, a cluster of negative trends in parts of the southeastern US into the Tennessee Valley, the Cumberland Valley, in parts in Pennsylvania, northeastern US, into the Ottawa Valley, those rivers draining into Lake Huron and Lake Superior, and then the Pacific Northwest and Columbia River system. Now, there's a few positive trends as well. So we see that actually the Humber River up in Newfoundland, but we also have unregulated rivers in parts of Newfoundland. I think the Gander River showing a positive trend. Those rivers, the Pirabanca especially, which is managed by Rio Tinto, showing positive trends. That drains into Lac Saint-Jean and then eventually the Saguenay River. We have the South Saskatchewan actually in Saskatoon, so just downstream of Gardner Dam with a positive trend. And a few other clusters, well, not necessarily clusters, but a few isolated positive trends as well. But the predominant pattern that we're seeing is a decline in terms of WHI across Canada and the USA. We're going back here to the WHI time series overall. So the overall mean, now focusing only on 1980 to 2019. We just wanted to check that it's this trend is not an artifact of missing data. So we have some sites where, particularly in 1990s into the 2000s, we had some missing data in Ontario and Quebec. What we did is we infilled those sites with the mean WHI over the period of record. So we have an original WHI time series in red, the adjusted value. There's not a lot of difference. So it's really not an artifact, at least we feel, that we're experiencing a negative trend in our WHI between 1980 and 2019. The linear trends are indicated by the dashed lines. Again, this is Mann-Kendall test, and both are statistically significant at a p-value of 0.05. And the decline is of, in terms of the magnitude, 0.4. So it's a fairly large decline in our WHI over that 40-year period. Okay, so let's try and understand what may be causing some of the negative trends that we've seen across USA and Canada. So let's look first at a possible relationship with perhaps a wet period. And why might that be important? So we have here the Colorado River at essentially Lee's Ferry. And this is just downstream of Glen Canyon Dam. Of course, upstream we have Lake Powell, which is a pretty large reservoir at 33 cubic kilometers. And the black line indicates the WHI, and then the discharge is indicated by the red line. You have to multiply the value by 10. And in the early 1980s, so 1982, 83, and then 83 to 84, we had a really strong El Nino. We had really abundant precipitation, particularly in the upper part of the Colorado River system. And that led to heavy snowpack and really large inflows into Lake Powell. And because of that, and because the reservoir level was going so high, they actually had to release water through the spillway, as well as through the bypass tubes in the spring of 1983 into the summer, as well as in 1984, because I believe precipitation was even higher in the winter into the spring, winter of 1983 into the spring of 1984. So because, of course, now they're releasing additional water through the spillway and the bypass tubes, in addition to generating hydropower, we see the WHI actually decreasing those years. And in fact, if we look at the 1987 and then 2011, those were El Nino years, we also see the WHI actually declining. This is also an important point that we wish to make, is that at hydroelectric facilities, it's important not to only get the amount of water that is turbined, but also get the amount of water that is essentially spilled, if there's a spillway at that facility, and to get the total volume of water. If we were trying to represent essentially the hydropeaking cycles that we're observing downstream from the hydroelectric facilities. As well, what we did was did a cross correlation between the WHI and the annual discharge over 1980 to 2019. And we saw a predominance of negative correlations or anti-correlations. I think it was close to 100. So high flow years indicate low WHI and vice versa. Well, another interesting point that we wish to make here is that there may be some water management factors that are coming into play. We're looking here at essentially the deviations in terms of day of the week flows on a given year for the Churchill River in Labrador at Churchill Falls Powerhouse. So remember, we saw a time series of the WHI here with an abrupt decrease in the WHI, I think in 1997. So the days of the week are shown by the colors. The black represents Sunday. Again, because of hydropower production is diminished on the weekends, you see a really negative and a large negative deviation, particularly in 1980s and 1990s on Sunday, as well as at Saturday, but not as pronounced on Saturday, which is the magenta color. The other days of the weeks, well, these are weekdays, and so we tend to see above the weekly mean values in terms of the deviations. And then the standard deviation across the 7 days of the week is indicated by the cyan color. And the greater the disparity between the days of the week, you see particularly in the 1990s, the greater, of course, that standard deviation across the 7 days of the week. Now, in 1990s, obviously there's an abrupt decrease in terms of the difference between the days of the week. So this is due to essentially changes in terms of the clients, from what I was told by folks working at Nalcor Energy, in terms of their demand in terms of hydropower. So this led to some rather drastic changes in terms of the disparity between the days of the week flows, and that led to a significant decline in the standard deviation across the 7 days of the week. Well, now we can actually do a similar analysis at all of the sites that we have data for. So we're looking now at the average standard deviation, or what we call the day of the week dispersion, at all 500 sites. This is based on 1980 to 2019. So the smaller black circles indicate really low deviations across the 7 days of the week, which is not unusual, of course, in Northern Canada, where we have very little day-to-day changes in terms of the flows, right? Whereas in the Southern US, we have pluvial rivers. For instance, we have the Santa Ana River in California, the Concho River in Texas, which max out at about 30 or more on our standard deviation scale. So pluvial rivers will tend to show larger fluctuations, particularly if they're smaller systems from day to day. But as well, regulated rivers will tend to show high standard deviation, tied in part because of hydropower production. And that is the case even in Canada, where regulated systems, for instance, we have the Columbia River, which is showing, at fairly high values relative to other systems that are not regulated in parts of Canada. Now, we can actually look at the trend in the day of the week dispersion. So we're looking at the standard deviation each year from 1980 to 2019, and then computing the Mankato test. And again, the blue triangles indicates a negative trend with the statistical significance indicated by circles. Again, the green circles indicate locally significant trends, the pink circles globally significant trends. And if you were to compare this map of the day of the week negative trends, they line up very, very closely with those essentially where we're experiencing a decline in WHI. So water management is certainly leading, changes in water management is leading to changes in not only the WHI, but also in terms of dispersion of the flows across the 7 days of the week. And these negative trends are pretty much, again, predominant across both southeastern US into parts of the Ottawa Valley, into northwestern Ontario, Manitoba, and in the Pacific Northwest. And the last result, before we get into a few points of discussion, is for the Peace River over 1980 to 2019. We're very fortunate here to have several Water Survey of Canada hydrometric gauges from, well, there's some in the headwaters, of course, but we're focusing on those downstream of both the WAC Bennett Dam and then the Peace Canyon Dam. If you look at the small inset map at the top left, we have the first gauge downstream, which is at Hudson Hope in northern British Columbia. Of course, we have Site C currently in development, which should come online later in this decade, which is just upstream of the confluence of the Pine River. And then we have other gauges at Taylor, Alsace, and all the way into Alberta, of course, to Peace Point, which is near the Peace Athabasca Delta and the confluence with the Slave River. And then we have another gauge at the Slave River, that's number 9. So we did a calculation of the WHI for 1980 to 2019. And the first 4 sites downstream of the 2 dams show values of WHI close to 1.4. So that signal is propagating all the way into Alberta, essentially. So the point number 4 is at Alsace. And then it starts diminishing. At 0.6, we're at the Community of Peace River. Now we're actually capturing the flows of the Smoky River as well as other tributaries from the Northern Rockies. So the score diminishes to 0.93. And then by the time we reach the Peace Athabasca Delta, we're essentially at a negative WHI. So we're losing that essentially signal by the time we reach the confluence of the Slave River. And indeed, the Slave River shows no evidence of hydropeaking. It is showing a score of minus 0.74. And the correlation between the WHI at Hudson's Hope with the downstream location shows that, of course, the correlation values tend to decline. The significant correlations are in italics, so a P of 0.05. So that correlation is significant up to the BC-Alberta border, but then we lose that significance as we move into Alberta. Also, just want to mention that the Peace River at Hudson Hope, we had pre-regulation a large negative score, minus 1.3, whereas after regulation, so essentially WAC Bennett Dam came online in the late 1960s, and then the Peace Canyon Dam came online in 1980, I believe. So we see then a switch from large negative numbers into positive values to 1.6. All right, well, a few points of discussion before we open it up for questions. Well, so what are some of the advantages of using WHI? So as we mentioned earlier, we can all find another paper that actually had focused on the weekly hydropeaking cycles, either in North America or elsewhere globally. So the advantage of our approach is that we make use of daily discharge only. There's no need for an extensive GIS databases like Grill et al., which make use of reservoir databases, dams. They also use hydrological models. So we only need, and our study, of course, as you saw, is based on observations. So we can use daily discharge. Of course, we could use reconstructed or model data as well, but that's an advantage, we feel, of our approach. It also eliminates the need for various metrics or indicators of flow alteration, regulation, or fragmentation. So there's been a lot of studies based on the work of Richter et al. Published in 1996, where they developed essentially 33 indicators of hydrologic alteration. So just using the WHI, we can actually get an idea of how regulated a system is, at least on a weekly basis. The other advantage, it is scale independent. It applies to both small scale and large scale operations. So when we described the 500 sites, forgot to mention that our smallest site in terms of gauge area is only 190 square kilometers. Our largest is actually the Missouri River at 1.8 million square kilometers. So we have several orders of magnitude in terms of basin scale, yet we can actually compare easily the WHI across those vast differences in terms of gauge area, as well as volumetric flows. It's dynamic, so we can actually compute the WHI on an annual basis. It will respond to wet and dry periods, changes in water management practices, as well as new dams that come online and decommissioning of old ones. And it's also relatively straightforward computationally. This is coded in Fortran actually, and to run it, the WHI takes about 4 minutes to essentially compute those time series from 1920 to 2019 of the 500 sites. And could be essentially applied for numerical modeling. And I think one of the arguments we want to make, because this is a modeling team, is that hydrological modelers will probably want to start considering hydropeaking if they're concerned about regulation. So we saw, obviously, in the rivers draining into Hudson Bay, that we have some really strong weekly cycles arising from regulation. So if modelers want to, get the best data, of course, for regulated systems, hydropeaking will be a feature probably they wish to integrate in their numerical models. And by using WHI, at least you get an idea of the intensity of those cycles in the regulated rivers. Well, what may be causing the declines in WHI? And we actually have a publication that hopefully will be soon resubmitted to a journal, and that tries to go at length in terms of describing some of the possible reasons. And there's quite a few. This is just sort of a list that we've brought up here. In the 2010s, we saw above average precipitation and discharge. And we saw, for instance, in the Colorado River at Lee's Ferry that because of the use of the spillway and the bypass tube during heavy precipitation years, that we saw a reduction in WHI. The 2010s, particularly in the upper Midwest of the US into the Canadian prairies, at least the eastern part of the prairies, we saw above average discharge. So maybe that is leading to a decline in WHI during the 2010s. We had some socioeconomic shifts, changes in industrial and commercial activities, so an expansion of that, for instance, on the weekends through Sunday shopping. Of course, that doesn't take into consideration what's happened over the past year with COVID-19. So that's an entire story that we really haven't addressed in our own study because we finish our study period in 2019, but perhaps is worth exploring in a future study. We also saw a shift towards other modes of electricity production, such as renewable resources, so wind, wave, and solar energy, particularly in the 2010s. So that might be offloading some of the production from the hydropower facilities. We also saw deregulation of electricity production and power grid interconnections. So we saw, for instance, with the coming online of the Churchill Falls powerhouse, and as well the James Bay hydroelectric facilities, that with the power grid interconnections into the US, they may actually have led to fewer sites exhibiting hydropeaking cycles, particularly in southern Quebec. And then legislative and policy changes affecting water management. So increased concerns for ecological, environmental, and cultural flows. And one of the facilities that we look at was the Prickett's facility for hydropower production in northern Michigan. And in that system, the state, Michigan State, mandated essentially that peaking power station to essentially become a run-of-river facility through a state policy. And that led to a rapid decline in WHI in that system. And the final point, well, there's been actually a lot of work on the ecological or eco-hydrological impacts of hydropeaking. So if you look at, for instance, the Web of Science and type in hydropeaking, you'll see a lot of studies focus on aquatic species, including fish and insects. So really good. Hi.
We are running a little bit over the time, so I was wondering if we can just leave the screen like that so people can read it and just give some chance for a few folks to ask some questions if they have
Oh,
something.
yeah. So why don't I just move to my conclusions, if that's okay, Praveen,
Yeah,
and
sure.
then we'll come back to this if there's questions on that. But sorry about that. I lost track of time. So in terms of our conclusions, well, we saw that weekly hydropeaking cycles are common features across Canada and US. Our WHI, we feel, actually captures this weekly fluctuation really well. So we feel this is probably important for power system operators, water resources managers, and hydrological modelers as well. So you might find our WHI as a useful tool to assess flow alteration. So that is it for my presentation. There's a lot of people to thank here. I won't go through the list, but we also want to thank our data providers. You see the list on the right, and I'll be more than happy to actually take any questions now. And thank you for the invitation to present today. Really appreciate it. Thanks to Global Water Futures for this opportunity. I really appreciate it. So that is my presentation. Sorry for going over time.
No problem. Thank you, Stefan. That was really a fantastic talk. So we'll be now moving towards question and answer session. So I'll just let the floor, I'll just open the floor for anybody to ask the questions and give them some moment to type in. In between, I just wanted to quickly ask for your study period, so 1980 to 2019. So all the study sites that you studied, were they all regulated before that period, or some were regulated, in 1990s or 2000? So if that was the case, then you have some cases where, it's all regulated, but some cases where you have natural flow and then regulated flow. So in this situation, if you had that kind of scenario, then how did you, address that? Because I have received this criticism in one of my past work that you cannot, if the period is not uniform, then you cannot directly compare or something like that. So.
Yeah, that's a very good question. So yes, some of the sites span periods pre-regulation and then post-regulation. So we saw that the WHI time series for major rivers in northern Canada, and of course we span periods pre-regulation where typically we would have negative WHI, and then post that. Now, between the 1980s to 2019, there's a lot of if very few dams came online, apart from maybe parts of northern Canada. So it's a fairly uniform stretch in terms of the hydropeaking intensity. In Canada, of course, we had the Churchill Falls powerhouse come online, and then that gone in the 1980s. But that's partly why we chose 1980 to 2019 as sort of our focus period, in that the amount of dams was relatively, of course, stable over that time. Now, of course, there's new facilities that are soon coming online on the Peace River, Site C, Muskrat Falls, and Labrador, of course, and Kiosk now that is partially online now on the Nelson River, and other systems in Quebec that are being developed for hydropower.
Thanks. Next question is from Mazda. It says, thanks for your very informative presentation. I was wondering if you have any idea about predicting the natural daily flow in the rivers with hydropeaking based on the WSI index.
Yeah, exactly. So I think this is something we would like to propose, is that if you have a WHI for a given system, and of course it will vary from year to year, but at least you would have an idea of the reduction of the flows on the weekends and the augmentation of the flows during the weekdays due to the hydropeaking feature. So of course, a lot of numerical models are not presently, at least, taking into consideration the hydropeaking feature. But if we have a WHI for a given river, let's say the Nelson River, and we know it's a 3.0, well, we can revert that back to essentially a weekly cycle and then augment the simulated flows on the weekdays according to that cycle, and then diminish the flows on the weekends appropriately. So we do think WHI would be useful in that sense, in giving us an indication of how much we have to adjust on a daily basis, perhaps the simulated flows.
Thanks. The next comment is from Al. Al says, nicely done. I suspect many of the attributes you listed as reasons for the change in the index are valid. So it would be very interesting to see which of those possibilities dominate. Encourage you to continue the work.
Yeah, great, thank you. Yeah, and one comment that actually could be made here is that we've seen some changes in WHI as well in parts like of Newfoundland, for instance. We feel this could be tied to perhaps less of a snowmelt-dominated system with the annual timescale more towards a pluvial system. It's actually affected our WHI, even though we focus, of course, on the weekends versus the weekday flows. But we might actually be able to use the WHI to look at regime shifts as well in terms of the hydrology of some rivers that are not affected by regulation.
Thanks. I don't see any other questions at the moment, and we are running 4 minutes past the time. So I'll just give a few seconds if somebody has any, last comment or question. So just maybe 10 seconds, and then if we don't have anything, then I'll formally close the webinar.
Well, thanks again. Thanks to the audience, and feel free to contact me. My email is sdery@umbc.ca. And the one thing I did not mention, there is a link here. So my co-authors and I have a paper currently under review at Nature Communications reporting these results and much more. It is the first draft that you'll see on the link there. It will be updated, but if you want to read more about it, that's available online. Again, feel free to contact me though if you have additional questions or comments. We welcome your feedback. Yeah.
And please raise hands if you are typing the question, because sometimes it takes time to write text and I could miss that. So I don't see any question at the moment, and my apologies for a little bit running over the time. And I want to thank you again, Stefan. I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. So just a note that next week I will be having Dr. Nandita Basu from the University of Waterloo. So please stay tuned. That will be all for today. And as Stefan mentioned, if you have any questions, please feel free to email him. And I'm sure he'll be happy to answer those questions. So that will be all for today. Please stay safe. I wish you a good day.
Thank you so much. Thanks again for the opportunity. Thank you, everyone. Have a good day. Okay, bye-bye.